Okay, next up, we have a tech talk. We're going to break up some of these panels with tech talks. It's my pleasure to introduce Dr. Jeff Prevost. Jeff is an associate professor in the Electrical and Computer Engineering Department in the Klesse College of Engineering and Integrated Design at UTSA. He's a cloud technology endowed professor, the vice president for secure cloud architecture for Symantec, which you heard Dr. Amy talk about earlier. And he's the executive director of UTSA's Open Cloud Institute. With extensive experience in industry before joining UTSA's world-class faculty in higher education, it's no wonder that he's leading the way in next generation technology at UTSA. Today, we're very fortunate and privileged to hear Jeff talk about some of his own research, specifically in the area of quantum, specifically revolutionizing healthcare, manufacturing, and critical infrastructure security through quantum. Jeff.
Thank you, Nicole. We know that cryptography is based on having secret key values that are used to encode and decode data in such a way as to hide original contents. Encryption hides, decryption unhides. Both functions require the correct common key. Keys are used in two different ways: symmetric, where keys for encryption and decryption are shared by participants, and asymmetric, where the key is split into a public and private part. The public part is used to encrypt, the private is needed to decrypt. As the name states, you share your public key and you keep hidden your private key. This allows anyone to securely share data with you without first having to find a way to secretly exchange this common key. RSA, the most commonly used asymmetric protocol, is based on the difficulty of factoring large prime numbers, an inherently computationally intensive task. Everything we know as e-commerce is based on asymmetric encryption. In 1994, Peter Shor provided the first solid motivation for researching in quantum computing. We refer to it as Shor's algorithm. This algorithm uses periodicity to factor large prime numbers. Recall, this is the basis for RSA asymmetric encryption. It was estimated in 2022 that it would take a theoretical quantum computer roughly 8 hours to calculate the factors for 2048-bit RSA. For comparison, the most powerful supercomputer would take well beyond the human lifetime. This quantum computer would need over 20,000 error-corrected qubits, the fundamental unit of a quantum processor, to perform this calculation. So to illustrate full-stack quantum computing, the top picture shows the Google Willow quantum processor with 105 qubits. Working at this layer requires fundamental materials science knowledge. The bottom picture is the quantum classical interface, which provides the cooling and control signaling to operate and read out the results of the quantum computation. Working at this level requires knowledge of engineering. NIST, which stands for National Institute Standards and Technology, the promoter of the current encryption standards RSA and AES, put out a call for an updated set of encryption standards a few years ago. The result is a new set of proposed standards that are thought to be immune to a large-scale quantum attack. This collectively is known as post-quantum cryptography. Instead of being based on factoring or elliptic curves, the new standards are based on a mathematical structure known as a lattice. These lattice-based protocols are not currently thought to be susceptible to currently known quantum algorithms and will hopefully remain so. The challenge is to implement these new standards in all devices and software that connects to the internet, not just people and web browsers. Think Internet of Things, IoT. Currently, there are approximately 18.8 billion IoT devices around the globe. It's expected that there'll be over 25.44 billion IoT devices by 2030. Each of these will need to have its encryption system swapped out for a new quantum immune version. The current generation of cybersecurity trained professionals do not receive training in quantum security concepts. Unlike quantum computing, quantum sensing is not a future promise, but is here today. In medicine, magnetoencephalography, or MEG, allows for non-invasive electrophysiological imaging of human brain activity. However, current MEG technology has significant limitations. You look at image A in the upper picture, the patient's head, if you can see, is in the cavity of the MEG device, which is kept at near absolute zero temperature via cryogenic systems. By exploiting quantum sensors, known as optically pumped magnetometers, or OPMs, the OPM MEG has the potential to dramatically outperform the current state of art, promising enhanced data quality, which means better sensitivity and spatial resolution, adaptability to any head size or shape, from babies to adults, motion robustness, participants can move freely around during scanning, and less complex imaging platforms without the reliance on cryogenics. Image B at the top and down below to the right shows patients wearing the OPM MEG helmet. Each sensor is shown on the far left in red, small and far less expensive than the prior version. Nitrogen vacancy centers are small defects in diamonds that are sensitive to external fields. Think of the brilliance you marvel at when you look into a diamond. This quantum effect has been successfully used for quantum sensors to aid in fields such as manufacturing and oil and gas explorations. Manufacturers historically isolated their manufacturing machines from the external environment through a process known as air gap. This prevented someone from tampering with the manufacturing process at runtime. However, the need for remotely available resources, think cloud computing, has driven manufacturers to violate this rule and provide access to the OT side of the system, the manufacturing floor, from the IT side, the normal business side. This has created opportunities for an ever-increasing set of attacks, often started by an employee clicking on a malicious email. Stuxnet, for example, represents one of the most widely known OT network attacks. The Cyber Manufacturing Innovation Center, the CyManI, here at UTSA, has been mandated by the Department of Energy to work on this very problem. Healthcare faces many of the same challenges that manufacturing does. The mandate for more efficient, portable healthcare has forced providers to exchange patient medical records via EMR platforms. In the drive for better clinical outcomes, healthcare increasingly relies on state-of-the-art technology such as quantum sensing. Remember the MEG from earlier? This pressure is largely increasing. The need to implement the post-quantum cryptographic algorithms for medical devices and systems is a daunting challenge for medical IT professionals, largely untrained in quantum security. They need assistance. The Quantum Institute for Cyber Resilience, QUICR, is our response to this grand challenge. This institute is proposed in response to the NSF's Quantum Leap Challenge Institute solicitation, which was successfully submitted here at UTSA this past Friday. We're asking the NSF for approximately $40 million over a 6-year time period. This is largely a Texas ecosystem stretching across the state. It brings together a vast network of state-of-the-art quantum research. UT Austin, UT Arlington, UT Dallas, University of Houston, Texas A&M, SMU, Baylor, Rice, University of Tennessee, Knoxville, and University of Tennessee, Chattanooga are just some of the major universities. Tennessee universities bring relationships that add significant value to the ecosystem, and they're the only other state in the South with significant quantum research. To date, there hasn't been any significant state or federal funding for large-scale quantum research in the state of Texas. We seek to change that. QUICR represents 3 primary research areas and 3 cross-cutting themes. Research areas include quantum mathematics, quantum devices, systems and networking, and quantum algorithms and computing. The three cross-cutting themes include quantum security, workforce development, and policy and ethics. Illustrating some of the recent breakthroughs in quantum information science and engineering, and like quantum sensing, quantum networking is real. The image at the top shows a functional quantum network built in Switzerland in the mid-2000s. This linked CERN with universities located in Geneva. On the bottom shows a commercially available node that the Swiss quantum network was built on by a company named ID Quantique. It performs quantum key distribution to securely exchange symmetric keys across the network, eliminating the need for RSA. We plan to extend the current test beds in the Quicker ecosystem with similar quantum communications networks for both research and education. Now, Texas represents a unique ecosystem, combines a growing population with a large set of university systems doing outstanding quantum-related research. The number of undergraduate and graduate students increases the opportunity to educate the population in both fundamental quantum and quantum-adjacent fields. Test beds, such as those available through the Simani and UT Health partnerships, allow for transformational outcomes to be evaluated in real environments. Cyber ranges at Baylor and UTSA provide a mechanism for showing how post-quantum cryptographic algorithms work in practice. Photonics labs and semiconductor facilities at UT Austin, UT Arlington, University of Houston, and UT Dallas allow for fundamental research to advance quantum sensing and computing. These resources provide hands-on learning for both students and professionals seeking training in quantum. Simani creates a practical means for transferring key outcomes from the laboratory into testing environments, where practical and implementable solutions can be discovered for manufacturing. Experience at Oak Ridge National Laboratory's manufacturing demonstration facility led to the creation of the Cyber for Manufacturing, the C4M facility located here at Port San Antonio. Here, researchers and students gather and work on state-of-the-art manufacturing systems in an environment not too different from a typical manufacturing floor. Successful models for workforce development have already demonstrated how to provide additional skills for working professionals. These lessons will help accelerate the outreach programs of Quicker to upskill cyber professionals with quantum information, science, and technology skills required to navigate in a world with quantum computing. C4M will be extended to include a quantum network for testing post-quantum cryptography, entangled state distributions, and quantum sensing. Partnership with UT Health San Antonio allows for the development of proving grounds to demonstrate practical post-quantum cryptography with the assistance of both researchers and IT professionals. Opportunities to develop real-world solutions to securing electronic medical records with companies such as Epic, one of the largest EMR solution providers, will ensure practical quantum outcomes are produced. Integrating quantum sensor networks can be explored for ways to enhance clinical outcomes, resulting in improvements in patient health care, as well as providing training for both students and practitioners. UT Health opens the door for practical healthcare solutions developed alongside both the medical research and IT support community. With over 40 researchers from 18 different universities, Quicker has an extensive research community. Leading quantum researchers such as Dr. Scott Aronson at UT Austin will help lead and guide the Quicker community towards obtainable goals. Experienced quantum research such as Dr. George Siopsis at University of Tennessee, Knoxville, bring fundamental quantum and impactful relationships with places such as Oak Ridge National Labs to Quicker. Dr. Michael Vasilev from UT Arlington will help Quicker through research advances in photonics, such as in a possible new class of avalanche photodiode that, if successful, will allow practical quantum networking without the need for cryogenics, both lowering the cost and complexity of operation. Other researchers around the state will participate in research activities ranging from developing new materials that can be implemented in quantum systems, providing lower susceptibility to environmental noise, to new classes of quantum and quantum classical machine learning algorithms that will fulfill information processing needs for the future. The variety of universities, companies, and laboratories and institutes that comprise Quicker are unparalleled and are ready to lead Texas and the nation into the world of secure and resilient quantum. In summary, quantum information technology represents a paradigm shift for many industries, including manufacturing and healthcare. There are currently not enough trained security professionals, computer scientists, and engineers necessary to deal with the newly evolving issues related to quantum. It is imperative that, as a country, we get behind this problem and find ways to ensure that quantum computers in the wrong hands will not have disastrous outcomes for the U.S. Quicker represents an effort to face these challenges through a statewide consortium of quantum experts across many different disciplines committed to providing first-class research that will address the problems through research outcomes, student training, and professional upskilling. Thank you.